In this chapter, we're going to focus on chemical equilibrium. The previous chapter we covered was kinetics, and it was covering this part of the curve. Notice in this part of the curve, the concentration of the reactants is decreasing, and so it's changing as the time is changing. The concentration of the product is also changing with time. However, there comes a time when the concentration of the product and the concentration of the reactant is not changing at all. So we have an equal rate at which the product and the reactant are forming. At this point, the system is said to be at equilibrium. When a system is at equilibrium, it does not mean that the concentration of N2O4 and NO2 are the same. However, this means that the rate at which we are forming N2O4 and the rate at which we're forming NO2 are the same. That's what we're going to be focusing on in this chapter. Now, suppose we have A reacting with B to form C and D, and we have stoichiometric coefficients A for A and stoichiometric coefficient B, small b for B, and small c for C, and then small d for D. The equilibrium constant, K equilibrium, would be the concentration of C raised to its coefficient times the concentration of D raised to its coefficient divided by the concentration of A raised to its coefficient times the concentration of B raised to its coefficient. Notice that the equilibrium constant is a ratio. It's approximately a ratio of the products divided by the reactants. Now, sometimes that doesn't work out that well. In the equilibrium expression, we can only express gases and aqueous species. That's because aqueous species and gases change in concentration as a reaction proceeds. However, solids and liquids do not change in concentration as the reaction proceeds. So there's no need for us to include them in the equilibrium expression. Now we're going to look at reactions and see how we can apply what we've learned to actual chemical reactions. In this reaction, we have methane reacting with water to form carbon monoxide and hydrogen gas. Notice we're multiplying the products. Carbon monoxide is being raised to the power 1 because we have 1 mole of carbon monoxide right there. Hydrogen is being raised to the power 3 because we've got 3 moles of hydrogen. We'll then divide by our reactants. Methane raised to the power 1 and water raised to the power 1 because we have 1 mole of methane and 1 mole of water. The previous example that we looked at had the reactants which were in gaseous form as well as the products which were gaseous form. So we included both reactants down here in the denominator and both products in the numerator. However, here in this reaction, we have solids as well as gaseous species. Notice we have white phosphorus reacting with oxygen to form phosphorus pentoxide. The equilibrium expression is going to include the gases or aqueous species if we had them. So we notice we have 1 divided by the concentration of oxygen raised to the power 5. That's because we've got 5 moles of oxygen. Notice the solids are not included in the equilibrium expression. The reason is solids tend not to change in concentration as the reaction proceeds, as well as liquids. However, gases and aqueous species change in concentration as the reaction proceeds.